So here we are on the February 27th. It's a Thursday, and we have in our schedule, you'll notice this is a buffer day. But to give you as much time as possible to view the video and work on problems and come back to me with questions if you have them, I want to start the review today rather than wait till the scheduled time for the review. We use the buffer. And if we can finish the review today, that's all the better. Then that'll give you a week from today that the exam 4 will be due. So, but if we don't finish, that's not a great tragedy because we have next Tuesday to finish up the review. All right, so I'm working from the review document, which you would get hard copy in class or it's in Brightspace under the exam 4 module. And I've highlighted some problems that I want to be sure and get to. And if anybody zooms in or shows up in person, then my policy is always your problems come first. We fix your problems, and then if there's time left, we look at my highlighted ones. But I highlight them to give you a taste of what you can expect for an exam and to cover all the major topics. So, number one. And let's see, I don't think these are subdivided into chapters, so I can sequentially number them. Quick survey here. Okay. Yeah, they're sequentially numbered, so I don't have to identify the chapters. Number one, which of the following statements is not true of balancing a chemical equation? Remember, balancing a chemical equation requires that the equation does not violate any of the chemical laws that we understand up to this point. Particularly in this case, the law of conservation of mass that was given to us by Antoine Lavoisier. And in order to maintain the mass, in other words, the mass of the reactants is equal to the mass of the products. And we also know that atoms cannot be created or destroyed. So the number of atoms on the reactant side of any given element must be equal to the same number of atoms on the product side. That will preserve both the mass and the chemistry. Well, the elements, it will preserve the elements for that reaction. So if we look at A, subscripts in the reactants must be conserved in all the products. No. The first thing you do when you write a chemical reaction is you write the compounds or the elements, as the case may be, correctly and put them in their positions of reactants and products. And once you've written those compounds correctly, you cannot touch the subscripts. The only way to balance the elements after that point is by coefficients. So A is not true. And if A happens to be the only one that's not true, then as indicated there, A should be the answer. We look at the others. B, coefficients are used to balance the atoms on both sides. Yes, that's true. So B is true. C, phases are often shown for each compound, but are not critical to balancing an equation. In the vast majority of cases, the phases don't matter to balancing an equation, and they absolutely don't matter for this course. The law of conservation of mass must be followed. I've already mentioned that. Atoms are neither created nor destroyed during any chemical reaction. I already indicated that. So the only false one in that whole list is A. Now I crossed out C because that's not appropriate for these chapters. So we'll just move on to number 3. When the following equation is balanced using the smallest possible integers, what's the number in front of the substance in bold type, which is hydrogen chloride? So if we have PCl5 plus water yields H3PO4 plus HCl. Okay, if we use our budget method, then we would take each of the elements, and notice this is a polyatomic ion, but it's not the same on both sides, right? So we can't use that as a balancing group. That means we have to have individual elements for our budget. Chlorine, hydrogen, oxygen. There we go. Okay, so we just do an initial tally. There's 1 phosphorus, there are 5 chlorines, 2 hydrogens, and 1 oxygen. Sometimes I just count them up to be sure I didn't miss anything. So that's 1 plus 5 is 6, 7, 8, 9. 5, 6, 7, 8, 9. We're good there. Okay, on this side, we have 1 phosphorus, we have 1 chlorine, we have 3 hydrogens. Oops. Nope, we have 4 hydrogens. Okay, I'm going to need this. That's better. Right, 3 plus 1 is 4, and then 4 oxygens. Okay. So we don't have any elements separate from all the other reactants and products, so we can't use that holding anything to the end. We generally hold water to the end, but not all the time. We just don't want to start with water. So I would start with chlorine. We can get 5 chlorines with a coefficient of 5. That gives us 5 chlorines. It also gives us 5 plus 3 is 8 hydrogens. Go. Okay, now what do we do with the hydrogens? Well, if we want 8 hydrogens on this side, we need a 4 right there. So that makes 8 hydrogens, but it also changes the oxygens to 4. And we can see at an instant, 1, 5, 8, 4. This equation is now balanced. And the coefficient in front of the bold type, which is this one, is 5. That answer is D. Okay, that's the budget method for balancing equations. Okay, let's see, number 4. All the following are clues that a chemical reaction has taken place except. So we have A, B, C, D, and E. The first one is a solid forms. That's definitely a clue. That's called a precipitate. That one's true. The reactant is smaller. Now, how do you tell if the reactant is smaller? Well, sometimes it's impossible, right? Especially if it's in solution. You can't tell if you've lost a reactant. So that's not generally considered a good indicator of a chemical reaction. Bubbles form, yes. Formation of a gas. Color change, not always a chemical reaction, but a clue. And a flame occurs. Flame usually indicates a chemical reaction. So B is the answer. The reactant is smaller. There's no practical way to follow that one, at least with limited. I guess in some cases you could follow it with sophisticated equipment, but It's not generally accepted as a clue. All right, number 5. When the following equation is balanced using the smallest possible integers, what is the number in front of the substance in bold type? Okay, so here we have another one. Aluminum plus Fe3O4 yields aluminum oxide plus iron. Okay. Now these are both elements, these two. So we hold one or both of them till the end. And let's see if this one is written correctly, right? Oxygen is -2 in compounds, so that's -6 total. That's +6 to balance. And then 2 of them means that each one has to be a +3. So that works. How about this one? -2 is -8, so we need a +8 to balance. How do you get a +8 out of 3? Subdivide 8, it would be 8/3, right? 8/3. That doesn't happen. Okay. So the reason I did that was to show you that this is a valid formula, but it has to be given to you because it's not easily discerned what it is. And what we've discovered is actually it's a combination in the crystal of the solid. It's a combination of these two formulas. So now we have 3 irons here, and we have 4 oxygens there, right? And these do give you whole number. This would be a +2, and this would be a +3. But balancing the equation will still work just fine the way it's written. So let's get rid of these and balance this equation. We should be able to do this without the budget. If we have, but I think we better do the budget. So let's say aluminum, iron, and oxygen. So we have 1, 3, 4, and 2, 1, and 3. So that's 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 4, 7, 8. Okay. So we don't want to start with, well, we really don't have a choice because aluminum, iron are in both, but we do want to put our coefficients in front of one of these. So oxygen is common to these, and it only occurs in these 2 places. So how do we get 3 and 4 reconciled? We use the trick that I showed you, cross multiplication. So if we take that 3 and put it here, and this 4 and put it here, now we get 12 oxygens here and 12 oxygens there. But that also changes the iron. Iron is now 9, and aluminum is now 8. Okay. So, oh, excuse me. That's not right. Aluminum is 8. There we go. All right. So now that we've got the oxygen settled and we can reconcile the iron and aluminum by putting an 8 over here, that gives us 8 aluminums. And we put a 9 over here. That gives us 9 irons. So we have 8, 9, 12. That equation is now balanced. And the coefficient in front of iron is 9. So we had to use that trick where we cross multiplied to get the oxygens to behave. All right, number 6 coming up. Which of the following statements about chemical reactions is false? Okay. First statement, in balancing a chemical equation, all subscripts must be conserved. That's as false as it can be. The subscripts are based upon the correct formula for the compound. Either you're given the formula or you know how to write the formula from its name. And then once you've written it, then those values, those subscripts are fixed, and it doesn't matter what happens to them on the product side. The only thing that matters is the number of elements. Number of atoms of each element on either side of the equation must be the same. So A is definitely false. So that means B through E should be true. The subscripts in a balanced equation tell us the number of atoms in a molecule. Yep, B is true. C, when one coefficient is doubled, the rest of the coefficients in the balanced equation must also be doubled. Once the equation is balanced, then the ratio, the coefficient ratios, those numbers in front of the compounds and free elements are fixed. That ratio is fixed. But you can modify it by multiplying or dividing by some number, some whole number through the entire equation. The ratio then is not altered. So C is true. Once you balance the equation, you can multiply through by a constant factor. D says an individual coefficient in a balanced equation is meaningless. An individual coefficient in a balanced equation is meaningless. I think what's meant by that is the coefficient by itself doesn't tell you anything about the balance of the equation itself. All the coefficients taken together in their respective positions are necessary to balance the equation. But an individual coefficient in a balanced equation doesn't tell you anything. They have to be taken together as ratios. So that being said, D is essentially true. The phases in a chemical reaction tell us the nature of the reactants and products. Yeah, that's true. Right? It could be a solid, could be a liquid, could be a gas, it could be an aqueous solution. Those are the only ones that we use in this course. Number 7. When the following equation is balanced using the smallest possible integers, what's the number in front of the underlying substance? So we've got C2H6, which is a gas, and we have oxygen, which is a gas. Notice I left a gap here. That should give us carbon dioxide and water. And water, is this standard? No, this is under conditions of the reaction, water is going to be a vapor. Why? Because this reaction is a combustion. It's exothermic. In other words, it gives off a lot of heat, and that keeps water in the gas phase. Okay, so we're looking for the coefficient in front of that. We do need to use the budget for this. So carbon, hydrogen, oxygen. 2 carbons, 6 hydrogens, 2 oxygens. Over here, 1 carbon, 2 hydrogens, and 3 oxygens. Okay. We're not going to do the oxygen yet. We'll either do carbon or hydrogen. I'm going to start with carbon. So if we put 2 over here, that gives us 2 carbons, but it changes the oxygens to 5. Okay. Now we can go to the hydrogens. We need, excuse me, 6 hydrogens on this side, which means 3 here. 6 hydrogens. Now we have 4 plus 3 is 7. 7 oxygen. Now we've got carbon hydrogen balanced. We can do oxygen here. But notice this is an odd number, actually a prime number, and this is an even number. So we have to use our fractional trick. 7 halves. So 7 halves of O2 is 7 oxygens. Now we can get rid of the fraction. This ratio is fixed. 1, 7 halves, 2, and 3. We can multiply by 2. And if we do that, that gets rid of this fraction. It makes this 2, makes this 4, it makes this 6. Okay? So the coefficient in front of oxygen is 7. All right. How about another balancing equation? We want the coefficient in front of the water. So let's do number 10. Al2O3, aluminum oxide. We're given the phases. Yeah, that's a solid. Plus H2SO4 aqueous. That would be sulfuric acid. And aluminum sulfate. Should be 3. This should be 2 in aqueous solution. And water. Okay. So, what drives this reaction? More than likely, the formation of water will drive that reaction. We've got a sulfate on this side and a sulfate on that side. We can use that as a balancing unit. So let's do our initial tally. Aluminum, oxygens, and these are oxygens separate from the sulfates. And then hydrogens and sulfates. I'm just leave the charges off. Okay, so we have 2 aluminums here. We have 3 oxygens separate from the sulfates. We have 2 hydrogens and we have 1 sulfate. So that's 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Aluminum on this side is 2. Let's see, oxygens separate from this is 1. And hydrogens, 2 hydrogens. And sulfates, 3. Okay. So, we could do oxygens or hydrogens. I think I'd like to start with sulfates. Where to start is more a developed intuition over time as you learn to balance more and more equations. And I think sulfate will give us a better start. So if we put a 3 here, that makes 3 sulfates and changes the hydrogens to 6. Okay. Then we want to balance I think the hydrogens ought to come next. So we'll put a 3 here. And that'll get us 6 hydrogens, but it also changes the oxygens to 3. 2, 3, 6, 3. That equation is now balanced. And the coefficient in front of water is 3. All right, got another one. A lot of equation balancing here. Okay, what was that one? Number 11. Okay, we have 10. No phases in this one. Reacting with sodium hydroxide yields sodium stannate. Go. And leaves hydrogen. We want to know what the coefficient in front of the hydrogen is. Let's see if I wrote that correctly. Yes. Okay, so we set up our budget. There's 10. There are no polyatomics in here that are intact on both sides. That's a polyatomic, that's a polyatomic, but they're created or destroyed in the process. So we have sodium, then we have oxygen, and then the hydrogen. So we have 110, one sodium, one oxygen, one hydrogen. Over here we have 110. We have two sodiums. We have two oxygens and two hydrogens. Let's see, that's 2, 4, 5, 6, 7. 2, 4, 6, 7. Okay. So now where do we start? Well, if we can, we want to leave the 10 and the hydrogen till last. So if we focus on the sodium, that means I would put two sodiums here, a 2 coefficient there, two sodiums, now two oxygens, and two hydrogens. And lo and behold, we're balanced with one coefficient. What's the coefficient in front of the hydrogen? It's understood to be 1. That's why the answer is A. There are several other for you to practice if you wish. Another one I had to throw out. Excuse me. Let's see. These must be a little more difficult because they have higher point value. All right. Number 24. When we balance this equation, what's the number in front of the underline? So silver nitrate is our focus here. Lead solid plus silver nitrate in aqueous solution. And that gives us lead nitrate. Actually, lead 2 nitrate and silver solid. See, I better leave some room there. There we go. This has to be in solution. We left out the phase for this one. Let's put it in. That would have to be in solution. There we go. Excuse me. So we have nitrates that we can retain as balancing units. And we have, actually, this equation is we can do this without the budget. Notice that one nitrate here, if we have two nitrates here, now we have two silvers needed, and we still only have one lead. So one lead, two silvers, and two nitrates, and we're balanced. Now you can use the budget, that's fine. But if you do these things enough, sometimes you don't need the budget. At least not on the board or on paper. You can do the budget in your head. So the answer then is B. Coefficient of silver nitrate is B, is 2. There's another throw out. And we got several to go here. Several practice problems. Okay, for this one, this steps it up a little. This is a word problem that gives you the names. It gives you the names of the reactants and products, and you have to write them. Otherwise, you cannot balance the equation. Now, the equation balanced is right there, of course, but how did I get there? We're going to react iron 3 oxide. This is 33. iron, 3 plus, oxide, which is 2 minus. How do we balance that? We put a 2 here, put a 3 there. Okay. You don't have to have the phases in here to balance. So I'm going to leave them out. That's a type 2 compound where we're given the charge for the metal. Carbon monoxide is a type 3, 2 nonmetals. So carbon monoxide. And that yields iron metal plus carbon dioxide. There you go. You have to be able to write those formulas from the names. Otherwise, you cannot answer this question. Okay. So, let's see. We should be able to balance this equation. That's 3, 4. Now let's do the budget. I think we need the budget in this case. Oxygen and carbon. We have 2 irons, 4 oxygens, and 1 carbon. On this side, we have 1 iron, 2 oxygens, and 1 carbon. Okay. Now, we're going to hold the iron till last, of course. But notice a problem arises when you have elements in 2 different locations or more than 1 location on one side of the equation. And then that presents a problem. So we need to focus on the carbons and the oxygens. The oxygens in this case, 4 and 2. If we just put a 2 here and give us 4, then that balances this, but it throws the carbons off. Right? Now, we should be able to do that and then work back through it and get it fixed. And maybe that's what we should do the first time through. So if I put a 2 here, that gives me 2 carbons and 4 oxygens. But now I need 2 carbons on this side. Right? So that gives me 2 plus 3 is 5. Okay. So we're still messed up. All right. What if we bump this up 1? What would that do? Well, notice this is 2 plus 3 is an odd number. We need an even number. So if we go up to 3, then that gives us 3 carbons, and 3 plus 3 is 6 oxygens. Now we can change this one to 3, and that gives us 3 carbons and 6 oxygens. Then all we have to do is balance the iron. So it took a little finagling to make this thing balance out. I focused on arriving at an even number. That allowed me to work through changing this to 3 instead of 2, so that I have a 3 plus 3 is 6. Okay. So that gives you the balanced equation as you see there on the page. All right. This one is given to you, so you don't have to write the formulas from the names. But suppose I change the nature of this problem. And I said, balance the equation of silver nitrate plus calcium chloride yields silver chloride plus calcium nitrate. Right? Then you'd have to write the compounds. Right? So 39 would be, I'm going to leave the phases off just for brevity. Silver nitrate, that's a -1. This is a +1. Calcium chloride, +2, -1, so we need 2 of those. And that yields silver chloride precipitate. Okay, well, maybe it is important. Let's go ahead and include the phases. Since we have two solutions coming together to make a precipitate plus a soluble compound of calcium and nitrate. There we go. That's proper. Okay. We've got nitrate on both sides. We've got, and the rest are elements. So these typically, not always, but typically these precipitation reactions are very easy to balance. So notice you got two nitrates over there. If we put a 2 here, that gives us 2 nitrates. It also gives us 2 silvers. 2 silvers now, 2 chlorides, 1 calcium. This equation is balanced without going through the budget process, at least on paper. Okay, this one might be a little more trouble, so we're going to use a budget on this one. Number 40. All right, we got magnesium nitride. Okay, that's a solid plus water yields ammonia, which is a gas, and magnesium hydroxide solid. Excuse me. So we've got one solid here. All we have to do is add water, and it decomposes into ammonia and magnesium hydroxide solid. Okay, let's balance this one. We don't have any polyatomics that maintain, so we have to do each one separately. Magnesium, nitrogen, hydrogen, and oxygen. And our tally, 3, 2, 2, and 1. And on this side, magnesium 1, nitrogen 1, hydrogen 2, and oxygen 2. Okay, we don't have any elements standing out. These elements are all separate. We don't have them in 2 different places. Hydrogen's in 2 different places. That could be a problem. But currently the hydrogens are balanced. So we have to start someplace else. How about we start with magnesium? That means a 3 here gives us 3 magnesium. It also gives us 2 times 3 is 6 oxygen. Okay. And 2 times 3 gives us 6 hydrogens. Oh, 6 hydrogens plus 3 is 9 hydrogens. Oh, that was a wrong tally. That's 3 plus 2. Originally it was 5 hydrogens. But now it's 6 plus 3 is 9 hydrogens. Okay. How about oxygens? Right, we got 6 over there. We need 6 over here. Only occurs in one place. So 6 there would give us 6 oxygens. It also changes the hydrogens to 12. And now we can balance the nitrogens with a 2. Right, 2 nitrogens. That changes the hydrogens to 2 times 3 is 6, plus 6 is 12. And there we're balanced. I think that's, yeah, that's proper. Okay, that was number 40. some of these are going to seem impossible. And those that seem impossible are probably ones that you've never done before. So if you've never actually attempted these, then they're going to look like a foreign language. That's why you need to try to balance as many equations as you can get your hands on. And that's also why your review document has so many of them. We may be skipping a few, but I guarantee you will appreciate balancing as many of these as possible. Let's see, we're going to go down to this one. Hydrochloric acid plus calcium hydroxide, which is an acid-base reaction. Acid-base reactions tend to be easy to balance. Hydrochloric acid plus calcium hydroxide and acid-base reactions tend to be driven by the formation of water. Excuse me. Okay. Excuse me. We can go ahead and use the budget here. Hydrogen, chlorine, calcium, oxygen. So we have 1, 2, that's 3 hydrogens, 1 chlorine, 1 calcium, and 2 oxygens. Let's see, 1, 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7. Okay. Hydrogens, 2. Chlorines, 2. Calcium, 1. And oxygen, 1. Excuse me. If we hold the water to last and focus on, say, chlorine, we got 1 here and 2 over there. So to make 2 chlorines, we do that. That changes the hydrogens to 2 here, 2 there is 4 hydrogens. Okay. Calciums are okay. Oxygens and hydrogens need to be balanced. So if we got 4 hydrogens on this side, a 2 in front should give us 4 hydrogens. It also changes to 2 oxygens. And we're balanced. Right? And who's next? Okay. How about this one? Let's see. Sodium borohydride. Sodium borohydride, which is 4. And then boron trifluoride yields sodium borofluoride and B2H6. Go. Okay. So let's do a budget for this one. I think since we have boron in 2 places here, boron in 2 places there, it's probably going to be a good idea to have a budget. Sodium, boron, hydrogen, and fluorine. Yep, that's everybody. So there's 1 here, 2 borons, hydrogens, 4, and 3 fluorines. 1 sodium here, 1, 2, 3, 3 borons, and hydrogens are 6, and fluorines are 4. Let's see if I got that right. 1, 2, 6, 7, 8, 14. That's 4 and 10 is 14. And this is 1, 2, 6, 7, 10. So that's 7, 8, 9, 10. Okay, we're good. Now, where do you start? Well, I'd like to get those borons balanced if I could, because there are 2 here and 3 there. The problem is the boron occurs in 2 places on both sides. So I think we probably ought to leave boron and do something else first. Maybe the hydrogens. We do the hydrogens first. Right? If we multiply this one by 2, that makes 8. And now we can't get 8 out of that one. So if we multiply this one by 3, that gives us 12 hydrogens. And I'll get the rest in just a second. 12 hydrogens here, and then a 2 here would give us 12 hydrogens there. Okay, that takes care of the hydrogens. Now let's retally. 3 sodiums. 3 plus 1 is 4 borons. And let's see, hydrogens, we did that already. Sodiums, borons. Okay, that's good. Now on this side, we took care of the hydrogens, but we didn't do the boron. So that's 4 boron. Okay. So the borons are taken care of, but now we have sodiums that need to be dealt with. We need 3 sodiums on this side. Hopefully that won't mess up our boron count. Let's go ahead. 3 sodiums. Now that gives us 3 plus 4 is 7 borons. Okay. And 12 fluorines. Right? 3 times 4 is 12. 12 fluorines. Okay. Now, let's focus on the fluorines. Right. We could say, let's balance the borons, right? But that's a 4 and a 7. So what if we focus on the fluorines? That might make things simpler. If we have 12 fluorines, then how do we get 12 fluorines here? We multiply by 4, right? So that gives us 12 fluorines. Now let's retally. That's 3 borons and 4 borons is 7 borons. And that's balanced, right? 3, 4, 3, and 2 is balanced. That one was a challenge. All right, let's see. We skip a few. Come down to this one. 61. Okay, we're given the C3H7OH. That's propanol, I think. C3H7OH. Yeah. C3H7OH. Okay, it's a liquid. Plus oxygen. So this is a combustion reaction. And it should produce carbon dioxide and water. Okay. So let's see if I got those written correctly. All right. Now let's do a budget. We don't have any polyatomics, so we have carbons, hydrogens, and oxygens. That's it. Okay, 3 carbons, 7, 8 hydrogens, 1, 2, 3 oxygens. And on this side, we have 1 carbon, 2 hydrogens, and 3 oxygens. So we're going to hold the oxygens till last. They may be balanced now, but they'll go out of balance pretty quick. Let's see if I got it counted right. That's 11, 14. That's 10, 11, 12, 13, 14. That's 6. 1, 2, 3, 4, 5, 6. Okay. I didn't miss anybody. So let's start with the carbons. Whenever we have a combustion reaction with a carbon compound, I usually start with the carbons. So that means 3 here. That changes the oxygens to 6, 7. Okay. Then we look at hydrogens. I've got 8 hydrogens on this side. If I put a 4 here, that gives me 8 hydrogens. And 4 plus 6 is 10 oxygens. Okay. The tendency would be to put a 5 here and get 10 oxygens, but you still got 1 there. Okay. So let's see, 3. If we do, we want 10 total oxygens. So what I need is 9 oxygens here to add to that 1 oxygen there. So how to get 9 here? I get 9 halves. So that's 9 plus 1 is 10. Okay. So I use the fraction trick to give me just the number of oxygens I need to add to this 1 to give me 10. Now we got to get rid of the fraction. Times 2. So that takes care of the fraction. Then I put a 2 here, a 6 here, and an 8 there. Okay. So we have 2 propanols, 9 oxygens, 6 carbon dioxide, and 8 waters. And that equation is balanced. It was balanced before we did this, but it wasn't whole number. So we changed it to whole number by multiplying everything through by the same factor. Once the ratio is established, then you can do anything to the whole equation, multiply, divide, as long as every coefficient is multiplied or divided by the same number, then you still have the same ratio. Okay, here's one where you have to write the compounds. And I noticed that, subscripts. That one needs to be subscript. That one needs to be subscript. That one needs to be subscript. Oops. That. There we go. All right, so let's write the compounds from their names. Number 62. First reactant, iron 3 oxide. We did that one earlier. That's a type 2 compound. Iron 3 oxide, solid. Plus carbon monoxide. So now instead of pure iron, we're getting iron 2 oxide and carbon dioxide gas. There we go. Okay, now let's set up our budget. Iron, oxygen, carbon. We have 2 irons, we have 4 oxygens, and we have 1 carbon. On this side, we have 1 iron, 1, 2, 3 oxygens, and 1 carbon. Okay, where do we start? Well, we don't have any elements. So when in doubt, I'll just start at the top. So if we put a 2 here, that gives us 2 irons. And that changes the oxygens to 2 plus 2 is 4. Okay. And lo and behold, we're balanced. with one coefficient. All right, let's move it on down, pick up. Okay. Another combustion. With a hydrocarbon. Number 68. And we're working from a given equation. We call them hydrocarbons because the only thing they have in the molecule is hydrogen and carbon. So C8H18 is a liquid and oxygen gas. This is a combustion. And carbon dioxide gas plus water. Yes. Okay. If you drive a car, you're burning this every day. This is octane, the major component in gasoline. Okay, so where do we start? Well, I think we're going to need a budget. So let's tally first. 8 carbons, 18 hydrogens, 2 oxygens, 1 carbon, 2 hydrogens, and 3 oxygens. We're going to hold this one till last. Okay. And usually with hydrocarbon combustion, you can start with carbon. That seems to work. We'll put 8 here. That changes the oxygens to 16, 17. Okay. Let's see. Excuse me. Now we want to go to hydrogens. And 9 times 2 is 18. And that gives us 9 plus 16 is 25. Okay. Now we've got the carbons and the hydrogen bonds. We can do the oxygens. So how do we get 25 oxygens out of O2? We use a fraction. Okay. Now we want to get rid of the fraction. Just put a 2. 2, that means this is 18, 16, 25, and 2. So there's your balance. Okay, we've used up an hour. Let's look at 73. An aqueous solution of ammonium carbonate is allowed to react with an aqueous solution of nickel 2 chloride. What's the solid in the balanced equation? All right, if these are aqueous solutions, then the compound, which we have to write first, ammonium carbonate. There's ammonium and carbonate. That. So that means we need 2 of these in aqueous solution. And we combine that with nickel 2 chloride. So nickel with a 2 plus, chloride with a 1 minus, we need 2 of these. Okay. Now, to identify the solid, all you need to do is recognize that these ions are separate in solution. Carbonate, nickel, and chloride. Now, That doesn't, I'm not saying anything about a balanced equation here because we didn't identify the products yet. But if you combine the cation here with the anion there, you get ammonium chloride. And you look it up in your chart, your solubility chart, you find that this is soluble. Then you combine the carbonate with the nickel. Look that up, nickel 2 and carbonate in your solubility chart, you find that's a solid. There's your precipitate, NiCO3. Because this is a 2+, that's a 2-. 1 and 1 is all you need for that compound. All right, 75. A substance that, when dissolved in water, produces a solution that conducts electric current very efficiently is called. Well, any substance that causes water to be conductive is an electrolyte. But if it's very efficient, it's a strong electrolyte. Okay, so D is the best answer there. 76. The equation 2 silver oxide yields silver plus oxygen is a what type of reaction? Well, you're going from complex to simpler, right? We're going from a compound to its elements. That is a decomposition. But notice also that anytime you have an element in a compound on one side and it's a free element on the other side, that's always an oxidation reduction reaction. So you've got B and C, oxidation reduction and decomposition. Two of those are correct. So that's why A is the answer. Right? You could find either one in there, but they're both applied to this equation. 77. In what type of reaction is water always a product? Acid-base, every time. That doesn't mean acid-base reactions are the only reactions that produce water as a product, but water is always a product for an acid-base reaction. So E is the best answer for that one. How about this one? 80. Factors that most commonly cause chemical reactions to occur are all the following except. All right, so we had one similar to this very early on in our list. Which one does not indicate a chemical reaction? Right? A decrease in temperature. You can get a decrease in temperature from simply dissolving a salt, a chemical salt of some kind in water. That's how they make cold packs in the hospitals, right? You have a bag of water, and inside there's a breakable capsule with a compound in it, a salt. And you snap it and then mix it, and it gets cold. Okay? So that's a physical process. We still study physical processes in chemistry, but it's not technically a chemical reaction. All you've done is dissolve the salt. If you want to get the salt back, all you have to do is evaporate the water, and you get the salt back. No change in its chemical identity. So A is not an indication of a chemical reaction. Transfer of electrons, redox reactions, formation of water, acid base, formation of a gas, or formation of a solid, a precipitate. Those are all indications of a chemical reaction. A is not necessarily an indication of a chemical reaction. 83. I don't think we talked about 83 in class. I think it's in your textbook. The scientist who discovered the essential nature of acids through solution conductivity studies is Arrhenius. Arrhenius. We applied Arrhenius to the type of acid-base reactions that we were studying. All right, remember, an acid has at least one hydrogen in some other part of the molecule, and a base always has hydroxide in it. That's an Arrhenius acid and an Arrhenius base. All right, 84. An aqueous solution of ammonium sulfide is allowed to react with an aqueous solution of barium chloride. What is the coefficient of the solid in the balanced equation? All right, so here we've got multiple steps. We have to write the compounds correctly. Ammonium sulfide. There's ammonium. Sulfide. Sulfur is in the chalcogens. It's a oxygen group. And in ionic compounds like this one, sulfides are always 2-. So that means we need 2 of these. That's an aqueous solution. Okay. We're going to react that with what? Barium chloride. Barium, if you look on your periodic table, barium is an alkaline earth. It's a 2+ charge. And chloride is a -1, so we need 2 of those. Okay. So what will be the product? Well, if you do a double replacement, right, you swap ammonium for barium and make ammonium chloride, right, +1 -1, we find out that that's soluble. But if we combine barium and sulfide, we get a solid. 2+, 2-. So there's our unbalanced equation. Now we have to balance it. This one's very simple. Notice you've got ammonium here and ammonium there. We need 2 ammoniums here. So that gives us 2 ammoniums. It gives us 2 chlorides, and 2 chlorides. We have 1 sulfide, 1 barium, 1 barium. That equation is balanced. What's the coefficient of the solid? Coefficient of the solid is 1. Okay, 85. So what kind of reaction is this? C2H6 is ethane plus oxygen. That's a combustion reaction. Remember, this equation, the equation this is an oxidation reduction reaction. True or false, and why? Well, it's true. It is an oxidation reduction reaction. So we can throw D out, but we have to look at A, B, C, and E to say, okay, why is it an oxidation reduction reaction? Well, we can't just say that all combustion reactions are oxidation reactions, because that doesn't give us any one of the, that doesn't differentiate between A, B, C, and E. So we have to put the equation up here, 2C2H6 plus O2, how many O2s? 7 O2. Yields 4 CO2 plus 6 water. You know what? This might be a difficult one for you to answer because I don't think I'm going to extend the lecture to include determining oxidation states. Okay. And we'll use this equation as our sample. Okay, rule number 1. Elements equal 0 oxidation state. So the oxidation state here is 0. It's similar to, it's like analogous to no charge, but it can also be applied to covalent compounds as well and elements. So that's 0. If you're in a compound, then you're going to have a different oxidation state. Now, rule number 2, ions equal their charge. So if we have any ions in here, which we don't, then their oxidation state would be the charge on the ion. 3. Hydrogen equals +1 unless with a metal. So if you have a metal and a hydrogen, then the hydrogen is -1. Oxygen equals -2. Fluorine equals -1. And the sum of oxidation states equals 0 for neutral compounds. And the sum of oxidation states equals the charge for polyatomics. Okay, those are your rules. If you don't have these rules to start with, then you can't deduce the oxidation states for any of the other elements. Okay, so this one's 0. This one's +1, which means +6 total. We mean a -6 here, which means -3. -3 for that carbon. This oxygen is still -2, but it's -4 here, so that one carbon is +4. This is -2, and this is +1. Okay, so now we have the oxidation states for each of our elements. I like to draw tie lines. I draw a tie line from this carbon to this carbon. Carbon only occurs in one place on either side. So what has happened here? This has gone from a -3 to a +4. So how did it get there? It went from minus to more positive, means it lost electrons. It lost 3 to get to 0, and it lost 4 more to get to +4. So there's a loss of 7 electrons for each carbon. Okay. The oxygen went from here to here and here, and they're both -2. So each oxygen gained 2 electrons per oxygen. So now we know with oil rig Oxidation is loss. Reduction is gain. So who was oxidized? This carbon was oxidized. And this oxygen was reduced. Okay. Now we can answer the question. Yes, it is an oxidation reduction reaction. The rule of thumb is all combustion reactions are redox. But why? Well, the first one says the carbon is reduced. Carbon was not reduced, it was oxidized. So A and C are false. We could have B or E because carbon is oxidized. That's true. What's the difference between B and E? Hydrogen is reduced. Carbon is oxidized for B. No, hydrogen is not reduced. Oxygen is reduced. So E is the correct answer for 85. I know that's a lot to hit you with outside the lecture, but in order to answer these questions, you have to know how to do that. I'm going to leave these rules up here on the side because we'll probably have several more. 86. So we have this equation where we have, excuse me, zinc solid. Let's put it down here. Plus, let's see, silver nitrate. In aqueous solution yields zinc 2 nitrate plus 2 silvers. Okay. What's the question? How many electrons are transferred in the following oxidation reduction reaction? Right? Remember, if so many electrons come from an oxidized species, the exact same number of electrons must end up on the reduced species. So let's do our tally first. That's 0. This is a polyatomic that stays the same on both sides. So we can just say this is -1, this is +1. This is -1, this is +2, and this is 0. So nothing happened to the nitrates, right? They stayed the same. They're essentially spectators. But if we go from this zinc to this zinc, right? There was a loss 2 electrons per zinc. And there's only 1 zinc. So that's 2 electrons lost. This silver went from here to here. It went from a +1 to a 0. So it gained 1 electron per silver times 2 silvers equals 2 electrons gained. So the answer is 2. 2 electrons were transferred in the process. Total electrons. Right. Let's see. An aqueous 89. Some of these may not need this information, but I'm going to leave it up there in case we need it later. An aqueous solution of sodium carbonate is allowed to react with an aqueous solution of magnesium chloride. Aqueous solution of sodium carbonate. Carbonate is 2-, that's 1+, so we need a 2 there. that's aqueous solution, is allowed to react with magnesium chloride. Okay, so we're going to swap magnesium for sodium and make magnesium carbonate, which is a solid. And then we have sodium chloride, which is soluble. Okay, so there's our unbalanced equation. All right, the complete ionic equation contains which of the following species? In order to do the complete ionic, we have to balance the equation first. So we need two sodiums on this side, which gives us two chlorides, one magnesium, one carbonate. That's balanced. Now the complete ionic equation is two sodiums plus one carbonate plus one magnesium plus two chlorides yields the solid plus two sodiums and two chlorides. Okay. Now, which one of these species matches? You also notice from the answers, you have to include the coefficient. So two sodiums is not there, only one sodium. Two carbonates, that's not there either. Two magnesiums, nope, nope. One chloride, nope, two chlorides. Two chlorides, yes. E is the answer. This is the complete ionic equation. Okay. Identify the solid for 96. Right, we can do that fairly simply. I'm going to use a different method this time. So I'm going to put the cations across the top for ammonium sulfate and barium nitrate. 96. So we have ammonium here and barium there. And then the anions down the other side, which is sulfate and nitrate. That. There we go. All right. Ammonium sulfate was given, right? That's aqueous. Ammonium nitrate is also soluble. Just look it up in your chart. Barium sulfate forms a solid. Barium nitrate is soluble because it's one of the reactants. So the solid is barium sulfate. It's like that. 2 plus, 2 minus, one of each. So A is the correct answer for that one. $97. Okay, I put 97 in here so that you could get a taste of the type of question you might get in subsequent courses where they give pictures and you need to associate the picture with the reaction. So what's the reaction? Well, the reaction first is aqueous calcium chloride. Calcium chloride plus aqueous potassium sulfate. Okay. Yields what? Well, potassium and chloride would be here, and they're soluble. and calcium sulfate is insoluble. Okay? So now we need to balance the equation. We need 2 potassiums. That gives 2 chlorides, 1 calcium, and 1 sulfate. So that's balanced with just a single coefficient. Now, which one of these pictures represents this one? Well, this equation has a solid in it, right? So it can't be A. It has to be either B, C. It can't be E either. It has to be B, C, or D. They're the only ones with solid in them. Okay? If we also look at the side, the reactant, the product side, we find 2 potassiums and 2 chlorides in solution. Which one has 2 potassiums and 2 chlorides? This one only has 1 potassium and a chloride. This one has 2 potassiums and a chloride. So B is probably the answer. If we look at the reactants, 1 calcium and 2 chlorides, yep. And then 2 potassiums and 1 sulfate, yes. B is the answer because it's the best representation of the balanced equation. Let's see. Oh, types of chemical reactions. Here we go. How we do? We got a half hour. See if we can finish this. Classify the reaction given with the available reaction types. So we've got 2 cesium, let's see, 103. 103. We have 2 cesium and 1 fluoride. 1 fluoride gas yields what? 2 cesium fluoride solid. And that's balanced. Okay, what have we done? Well, we've performed a synthesis reaction. Also, elements to compounds means this is also a redox reaction. Okay. So it's both A and C. All right. That's 103. 104, let's put that down here, is sodium sulfate, lead 2 nitrate yields a solid. That's a precipitation. And we abbreviate that PPT, precipitation. Is it anything else? It's not an acid base, is it? No. Is it an oxidation reduction? Well, look at what you've got in that. I probably should have written it up here. Na2SO4 and PbNO3. Take it twice. So this is a 2+, this is a 1+, and the polyatomic ions remain intact on both sides. So we have to look at sodium and lead only. So as written, there's your precipitate, and there's your spectator. That's still a +1, and this still is a 2+. So it's not a redox. It's not oxidation reduction. It's not acid base either, right? There are no hydrogens in there. So it's only a precipitation reaction. C. Let's see, let's go down to 105. I guess I better write this one up there. 4 ammonias plus 5 oxygens yields 4 nitrogen monoxide plus 6 water. There we go. Okay, so let's see what our choices are. Oxidation reduction. Notice that oxygen ends up in compounds. So this is definitely a redox reaction. It's also a combustion. Okay. What else are we given? Oxidation reduction, combustion, yes. Synthesis, no. These are not any more complex than those. We're not creating a more complex compound from simpler substances. And it's not a decomposition either. So these two are the only ones. So the answer would be A and B for this one. 106. Let's see how far along we are. Okay. We might run out of time and have to pick it up on Tuesday. 106. All right, you've got a sodium and nitrogen making sodium nitride. That is a synthesis reaction, right? Is that one of our possibilities? No, it's not there. So what else? Well, we've got elements ending up in a compound. That's oxidation reduction. It's not acid base, it's not precipitation. Oxidation reduction is the only possibility here. 107. Use the following choices to classify each. Oh, okay, we'll just keep going. Mercury liquid and oxygen, that's also oxidation reduction. It's a synthesis, but that's not one of our choices. So this one is also oxidation reduction. About 108. Gallium nitride. Solid yields 2 gallium plus nitrogen gas. Okay. This is a redox reaction. It's also a decomposition. Complex to simple. It's not a combustion. It's not a synthesis. So oxidation, reduction, and decomposition, A and D, will be acceptable answers. 9. Let's see, what do we have here? Acetic acid. Plus what? Plus cesium hydroxide. Yields what? Water plus cesium acetate. Okay. Acid base produces water and salt. That's an acid-base reaction. About 110. Let's see. We have carbon oxygen yields carbon dioxide. Carbon solid, probably graphite, but it could be diamond. Okay. So what do we got here? We have a synthesis. we have a combustion, which is automatically redox. So synthesis, oxidation reduction is A, combustion is B, synthesis is C. It's A, B, and C. Okay. Here we go. 111. You should recognize this as an acid. Nitric acid plus sodium hydroxide yields water plus a salt. That's an acid-base reaction. Nothing else. 112. Let's see, KBr plus silver nitrate. All right, you've got two solutions here. You end up with a solid. That's a precipitation reaction. Those are not acid bases, and there's no change in oxidation state. Notice that potassium on both sides is +1. Bromine on both sides is -1. Silver on both sides is +1. And nitrate is intact. There has been no transfer of electrons here. So this can only be a precipitation reaction. All right, how about, okay, 113. We have two elements making a compound, calcium hydride, from calcium and hydrogen gas. That's a synthesis reaction, but that's not one of our options. But you have elements on one side in a compound on the other side, that's oxidation reduction. Now, we may have a solid as a product, but it's not a precipitate because it didn't come from an aqueous solution. Excuse me, 114. Let's see. Here we got another oxidation reduction reaction. It's also a combustion, but that's not a choice. It's not acid base and it's not precipitation. So oxidation reduction is the only possibility. Next one, 115. All right. How about this one? All right, we have zinc solid and hydrochloric acid. Yields zinc 2-chloride in aqueous solution plus hydrogen gas. Okay, we need two of those. That should be balanced. Okay, this starts off at 0 oxidation state, ends up at 2+ for that one. And we know that this one starts off at a +1 and ends up at 0 here. So we know there's been a change in oxidation states. That's a redox reaction, oxidation reduction. It's not acid base. Right? That's an acid, but that's not a base. So it's not an acid base reaction, and it's not a precipitation. We didn't form a precipitate here. So the only answer is A. How about 16? 116. We have sulfuric acid plus barium hydroxide yields water plus barium sulfate. Oh, that's a solid. Okay. Let's see if we got this balanced. I need two, let's see, Two hydrogens here, two there, that makes four. Sulfate's intact. And we have two oxygens and two oxygens here. Okay, that's balanced. All right, acid base, definitely. But also, when we put these two aqueous solutions together, we get a solid. So this is a precipitation reaction also. Acid base and precipitation. It's not oxidation reduction. There have been no changes in oxidation states. 2+, 2+, sulfate intact, hydrogen, 1+, 1+, oxygen, 2-, 2-. There's no redox evidence here. So it's B and C only. On 17. Let's see. We got zinc 2 bromide and silver nitrate yields zinc 2 nitrate and silver bromide solid. That is a precipitation reaction. We've got two solutions come together, we make a precipitate. And if you look at the oxidation numbers for each one, you find that it's not a redox reaction. We have not changed any oxidation states. And of course, it's not acid base. That's only a precipitation reaction. Simple. How about 118? Let's see, we have C3H8, which is propane, plus oxygen yields carbon dioxide and water. This is a combustion reaction because it has oxygen, which means it's also redox. Is redox in there? Yeah, oxidation reduction. We got those two for sure. Did we synthesize anything? No, or we didn't decompose either. So A and B are the only possibilities. Let's see, this is A and this is B. 119. We have phosphorus plus oxygen yields tetraphosphorus decoxide. Okay, we've undergone a synthesis. We've got elements going into compounds, redox reaction, and we've got a combustion with oxygen. So A, B, and C, all three are valid descriptors for this reaction. Similar situation for 120. Right, A, B, and C. We've got elements into compounds, we've got oxygen, combustion, and we've got synthesis. So A, B, and C for 120 also. How about 121? Let's see, we have mercury 2 oxide. Oh, decomposing into mercury liquid plus oxygen gas. There we go. Let's see. This is a decomposition. Okay. Elements, compounds. This is redox. Definitely. It's not a synthesis and it's not a combustion because oxygen's on the product side. So it's only these two, decomposition and redox. $122. Here we have hydrochloric acid and lead 2 hydroxide, which is a base. This is an acid-base reaction, but it also produces a precipitate. Lead 2 chloride is a solid in solution. It falls out. So it's both acid-base and precipitation, B and C. (123). Sodium plus hydrogen gas yields sodium hydride. This is a synthesis, and you have elements forming a compound. It's redox reaction. It's not a decomposition. It's not a combustion because there's no oxygen. So A and C, oxidation reduction and synthesis. 124. Right. Water decomposes. Right? So it's definitely decomposition. We're going from water to hydrogen and oxygen, but it's also redox. So we have A and D are possibilities. It's not a combustion because oxygen's a product. And it's not a synthesis because you can't have both synthesis and decomposition at the same time. At least not in this class. All right, let's see what else we got. Several practice problems there. Some of them more difficult than the others. And let's see. Here we go. I think 136. No, it just asks for the complete ionic equation for the reaction of barium hydroxide and aqueous hydrochloric acid. So barium, and these should be both aqueous solutions. So barium hydroxide, like that. And hydrochloric acid is like this. So barium and chlorine combine. Now, this should be 2. Now, is that soluble? Look it up in our chart, and it is soluble. Plus water. Okay. Now let's balance the equation. We got a barium on this side, a barium on that side. We got 2. Yeah. We got 2 hydrogens here. Actually 3 hydrogens, and we've got 2 over there. So if we put a 2 here, that makes 4 hydrogens, and a 2 here that makes 4 hydrogens. It also makes 2 oxygens and 2 oxygens here. So that's our balanced equation. Now, use your budget if you have to, but that is balanced. Now the ions, barium 2 plus 2 hydroxyl ions plus 2 hydrogen ions plus 2 chloride ions yields barium 2 plus aqueous, 2 chlorides aqueous plus 2 waters. Okay. So that should be the complete ionic equation. Now, while we're here, what's the net ionic equation? Well, we get rid of the spectators. Barium's in solution on both sides. All right. Chloride is in solution on both sides. The hydrogens and the hydroxyls are go into making water. So we can't cancel them because that's a molecule and these are ions. But if we write it like this, what do we do next? We have to simplify it, right? The ratio is 2 to 2 to 2, or 1 to 1 to 1. That's the net ionic equation for an acid-base reaction. All right, let's see if we can find another one here. How about this one? 138. I got 5 minutes. Maybe what I ought to do is just, oh, this is the last one. Okay, so we will finish up today. All right. So we have to give the molecular equation, the complete ionic equation, and the net ionic equation for this reaction. All right, so we start with the word problem, aqueous solutions of copper 2 nitrate. So copper 2 nitrate. That means we need 2 of these, because that's a -1, this is a +2. And it's combined with sodium hydroxide. Aqueous. So what's the product? Sodium nitrate is one possibility. That's soluble. And copper 2 hydroxide is a solid. So now we need to balance this equation. This is an, let's see. Nitrate's intact on both sides. Hydroxide is intact on both sides. That's good. So we know we need 2 hydroxides. That gives us 2 sodiums. So 2 sodiums here, 2 nitrates there, 1 copper. That's balanced. Now the complete ionic equation is copper 2 plus in aqueous solution, nitrate in aqueous solution, but there are 2 of them. Then we have 2 sodiums in aqueous solution and 2 hydroxyls in aqueous solution. Yeah, that's given out. Let's try this one. And then on this side, we have 2 sodiums in aqueous solution plus 2 nitrates in aqueous solution plus our solid. Okay, that's the complete ionic equation right there. Then we eliminate the spectators. Let's see, we've got 2 nitrates on both sides. And we have 2 sodiums on both sides. And the copper and the hydroxide go together to make the copper 2 hydroxide. That was given out too. Let's try another one. There we go. So there's your net ionic equation right there. Okay. All right. That's it.